In this lesson, we are going to look at aircraft magnetism, how it is acquired, and how it affects the accuracy of the magnetic compass. We will look at a compass swing and how a compass swing can remove or reduce the errors caused by aircraft magnetism. To conclude, we will look at the occasions when a compass swing should be carried out. The phenomenon which gives rise to the aircraft's own magnetic field is known as aircraft magnetism. Aircraft magnetism is acquired during the manufacturing process and subsequent use of the aircraft. It is caused by a combination of ferrous metals and electrical fields within the aircraft. Magnetism can be divided into hard iron and soft iron. Hard iron can be considered to be permanently magnetized and will make up the permanent magnetic field of the aircraft, whereas magnetism in soft iron will be induced only while there is an external magnetic force present. In theory, a magnetic compass should align itself with the Earth's magnetic field and point to magnetic north. However, an aircraft's own magnetic field will attract the magnetic compass away from magnetic north. The direction in which the magnetic compass points as a result is known as compass north. The angle between compass north and magnetic north is known as the deviation. Let's look at the effect of deviation. Suppose we imagine an aircraft is flying on a heading of 090 degrees in relation to true north. If the magnetic variation is 10 degrees west, the heading in relation to magnetic north will be 100 degrees. If we now say that deviation is 10 degrees west also, the compass will be showing 110 degrees as a heading. So to recap, deviation is defined as the angular difference between the direction actually indicated by a compass needle and magnetic north. Deviation is classed as easterly or positive, or westerly or negative, depending on whether the compass needle lies to the east or west of magnetic north. If we were to assume that deviation was 5 degrees east instead of 10 degrees west, the compass heading in our example would be 095 degrees. It is possible to remove a large amount of deviation error by appropriate calibration and correction of the compass. This process is called a compass swing, which we will look at next. To work out the amount of deviation being experienced, the aircraft's magnetic compass reading is compared with a magnetic datum compass. The comparison process is known as the compass swing, and the compass swing is carried out on an airfield in a location specifically designed for this operation. We can see the principle of the compass swing here. Initially, the datum compass and the aircraft compass are aligned with each other. The aircraft is then turned through 90 degrees. The compass heading is compared with the datum compass reading and the observed deviation recorded. The process is then repeated through 180 degrees and 270 degrees. The aims of the compass swing are: firstly, to observe and determine the deviations between magnetic north and compass north on a series of headings. Secondly, to correct and remove as much deviation as possible. And thirdly, to record the residual deviation which is left after a compass has been adjusted. Unfortunately, magnetic influences on the aircraft's magnetic compass are distributed all over the aircraft. Individually, they would be hard to locate and identify, so the solution is not necessarily to identify them, but merely to establish their total effect on the aircraft's magnetic compass reading. The total effect can be split into a longitudinal component and a lateral component. Deviation will vary with heading. Let's see why this occurs. Imagine that all of the aircraft magnetism is combined into a single isolated blue pole, which by definition will attract the red end of the aircraft's compass needle. Remember, like poles repel each other, unlike poles attract. Let us locate this blue pole on the longitudinal axis of the aircraft and in a position which is forward of the aircraft's compass. If we also create a graph, we can plot the deviation caused by the blue pole as we rotate the aircraft through 360 degrees. So let's look first at the effect the blue pole will have when the aircraft is heading north. The blue pole and the red end of the compass needle are aligned with the Earth's magnetic field, and so there will be no deviation. Let's see what happens now if we turn the aircraft onto a compass heading of 045 degrees. The blue pole is now out to the east of magnetic north, and so the compass needle will point, or be deviated, to the east. As the aircraft turns onto a compass heading of 090 degrees, the blue pole is even further out to the east. On this heading, the deviation effect has increased to a maximum because, if our aircraft now continues to turn onto a compass heading of 135 degrees, we can see that the blue pole is far less out to the east and the deviation has reduced accordingly. When the aircraft turns onto a compass heading of 180 degrees, the blue pole is directly opposite magnetic north, but because its effect is less than the Earth's magnetic field, there will be no deviating effect. Continuing the turn, deviation now becomes westerly, increasing to a maximum on a compass heading of 270 degrees, before reducing back to zero on magnetic north. Looking at the graph, we can say that the contribution to deviation from longitudinal aircraft magnetism is a function of the sign of the heading. The combined longitudinal hard and soft iron component of aircraft magnetism is known as coefficient B. Let's suppose we now locate the blue pole on the lateral axis of the aircraft, out on the right wing, and repeat the turn through 360 degrees. There is a maximum easterly deviation, with the aircraft heading north, as we can see. Following this through a 360-degree turn in a clockwise direction will result in a positive cosine curve. We can therefore say that the contribution to deviation from lateral aircraft magnetism is a function of the cosine of the heading. The combined lateral hard and soft iron component of aircraft magnetism is known as coefficient C. In practice, both longitudinal and lateral elements will be present and will combine to form the total deviation. We can therefore formulate an equation to calculate deviation on any heading, if we include one further factor. This factor is simply the contribution made to the total deviation should the aircraft compass be physically misaligned with the longitudinal axis of the aircraft, and it is known as coefficient A. The equation is therefore deviation on any heading equals coefficient A plus coefficient B sine heading plus coefficient C cosine heading. Coefficient B is the combined longitudinal hard and soft iron component of aircraft magnetism, and coefficient C is the combined lateral hard and soft iron component of aircraft magnetism. Let's work through an equation. So let's suppose coefficient A is plus 2 degrees and coefficient B is plus 3 degrees. And coefficient C is minus 4 degrees. And we will say the compass heading is 060 degrees. The total deviation on 060 degrees equals 2 degrees plus 3 degrees times sine 60 degrees minus 4 degrees times cosine 60 degrees, which equals 2 degrees plus 2.59 degrees minus 2 degrees equals plus 2.59 degrees. If we approximate 2.59 degrees to, say, 2.5 degrees, and if the pilot is flying a compass heading of 060 degrees, the magnetic heading is actually 062.5 degrees magnetic. Note that the deviation is applied in the sense that it is the correction required to convert compass heading to magnetic heading. If deviation is positive, magnetic heading is greater than compass heading. Error due to coefficient A is removed by turning the compass to realign the lubber line with the fore and aft axis of the aircraft. Let's say the error is plus 2 degrees. Error due to coefficients B and C are removed or minimized by creating local magnetic fields with additional magnets which are equal and opposite to the aircraft's magnetic field. Coefficient B is removed on headings of east and west. Let's say the error is plus 4 degrees. And coefficient C is removed on headings north and south, because as we saw from the graphs earlier, the relevant coefficients will be at their maximum on those headings. Let's make the error due to coefficient C minus 2 degrees. However, it is unlikely that all the deviation will be removed by this process, and therefore any residual deviation will be recorded on a compass deviation card, which will be placed adjacent to the aircraft compass. We can see a typical example here, and we can see that the compass is indicating 270 degrees or west. The compass heading is the magnetic heading plus or minus the deviation on that particular heading. So the deviation card is telling us that to fly an accurate heading of 270 degrees magnetic or west, we should steer a compass heading of 269 degrees. In accordance with EU OPS, residual deviation limits are as follows. For the direct reading magnetic compass, it is plus or minus 10 degrees. And for the remote reading magnetic compass, it is plus or minus 1 degree. Aircraft magnetism is influenced by the Earth's magnetic latitude and will actually change as magnetic latitude changes. Let's see why this is by looking at the effects of the Earth's magnetic field on hard iron and soft iron as latitude changes. Earlier, we saw that hard iron magnetism can be regarded as permanent magnetism and is not affected by external fields. So if aircraft magnetism due to hard iron does not change, what is it that causes deviation to change as latitude changes? The answer lies in the relative strengths of the Earth's Z and H components. We know from the lesson which dealt with magnetic dip that the Z component of the Earth's magnetic field will be at its weakest at the Earth's magnetic equator and strongest at the magnetic poles. Conversely, the horizontal component of the Earth's magnetic field, which we called the H component, reduces as the Z component increases. In other words, the H component will be at its strongest at the Earth's magnetic equator and at its weakest at the magnetic poles. Let's look at the effect this will have on deviation. We know that aircraft magnetism due to hard iron can be assumed to be constant, and we can represent this constant by the blue line here. As the directional strength of a compass needle is governed by the strength of the Earth's H component, represented here in red, we can see that deviation will be low near the equator, but will increase towards the pole as the effect of the H component decreases. We can say therefore that with hard iron, aircraft magnetism does not change with magnetic latitude, but deviation will change with magnetic latitude. Let's look at soft iron now. We know that in soft iron, magnetism will be induced when there is an external magnetic force present. This includes the Earth's magnetic field, and in particular, the effect of the vertical, or Z component of the Earth's magnetic field on the aircraft magnetism. As we know, the Z component will decrease and the H component will increase towards the magnetic equator. We can see therefore that deviation due to soft iron will be greater as magnetic latitude increases. Firstly, because the strength of the Z component increases, and therefore the aircraft magnetism increases. And secondly, because the horizontal influence of the Earth's magnetic field decreases, other external influences will have a greater deviating effect. We can say therefore that with soft iron, aircraft magnetism changes with magnetic latitude, and deviation changes with magnetic latitude. There are a number of occasions when a compass swing will become necessary. They should be noted, and they are: 1. When the compass components are installed or replaced. 2. Whenever accuracy of the compass is in doubt. 3. After a maintenance inspection if required. 4. After significant aircraft modification, repair or replacement involving magnetic material. 5. When carrying unusual ferromagnetic payloads. 6. When the compass has been subjected to significant shock. 7. After the aircraft has been given a new location to operate in, if the move involves a large change of magnetic latitude. 8. If the aircraft has been parked in long-term storage on a single heading. 9. In the event of a lightning strike. 10. After significant modification to aircraft radio and electrical systems. This concludes the lesson on aircraft magnetism. A summary of the main points follows. A summary of the main points of the lesson is: deviation is classed as easterly or westerly, depending on whether the compass needle lies to the east or west of the magnetic north meridian. The resulting direction in which the magnetic compass points is known as compass north. The aims of the compass swing are A. To observe and determine the deviations between magnetic north and compass north on a series of headings. B. To correct and remove as much deviation as possible. And C. To record the residual deviation which is left after the compass has been adjusted. The contribution to deviation from longitudinal aircraft magnetism is a function of the sign of the heading. The contribution to deviation from lateral aircraft magnetism is a function of the cosine of the heading. Deviation on any heading equals coefficient A plus coefficient B sine heading plus coefficient C cosine heading. Coefficient A is the contribution made to the total deviation should the aircraft compass be physically misaligned with the longitudinal axis of the aircraft. Coefficient B is the combined longitudinal hard and soft iron component of aircraft magnetism. Coefficient C is the combined lateral hard and soft iron component of aircraft magnetism. The regulatory residual deviation limits are plus or minus 10 degrees for a direct reading compass and plus or minus 1 degree for a remote reading compass. Hard iron aircraft magnetism does not change with magnetic latitude, but deviation does change. Soft iron aircraft magnetism changes with magnetic latitude, and deviation changes with magnetic latitude. The occasions when a compass wing may be necessary should be noted.